Welcome to this video from Derby Physics Tuition, and I'm working with a number of students at the moment who are studying thermal physics in year 13, and this video will concern deriving the kinetic theory equation. And in the AQA specification you need to be aware of the assumptions behind this equation, and also you should be able to derive this equation as well. So let's have a look at how we go through this. And first of all, what is the kinetic theory? And the kinetic theory model describes a gas as a large number of identical particles which are in constant rapid random motion. And in deriving this equation, we're going to assume that the gas behaves like an ideal gas. And in reality, real gases don't behave exactly like ideal gases, but their general behavior is close to the model of an ideal gas. And when we're deriving this equation, when we're using our simple model of an ideal gas, we make certain assumptions about the behavior of the particles, and you need to be aware of the assumptions that we make about the behavior of the particles. So let's have a look at the assumptions. Well, the first one is volume, and we're going to assume that the volume of the particles is negligible in the derivation of the equation. The second assumption is attraction, that there is no attraction between the particles, there are no intermolecular forces. The third assumption is random, that the particles are moving with random motion, they're moving with random speeds and in random directions. And the fourth one is that they are identical, all the particles are identical, and we are considering a large number of identical particles. And in terms of collisions, we're going to assume that the collisions are elastic, so there is no loss of kinetic energy in the collision. And the final assumption is duration, that the time between collisions is very much larger than the time spent colliding. And if you notice, the first letter of each assumption spells the mnemonic varied. So if you remember varied, that might help you to remember what the 6 assumptions actually are. So these are the assumptions that you need to be aware of. And so what we're going to do now is to move on to deriving the kinetic theory equation, and we'll be using these assumptions in the derivation of the equation. So we are going to consider a box, a container containing our gas, and we're just going to consider one particle which is moving in the horizontal plane. So here's our particle, and it's just moving back and forth in the horizontal plane, and it has a velocity u1 and it has a mass m. And we're going to consider that this box is a cube and it has dimensions Lx, Ly and Lz. Okay, now our particle is going to collide with the inside of the right hand face, and when it does there will be a change in momentum. And what is that change in momentum? Well, the change in momentum will be equal to the final momentum, take away the initial momentum, and the initial momentum is mu1. Now when the particle collides with the face, it will rebound and it will still have mass m, but it will be moving in the opposite direction, so its velocity will be minus mu1. So its final momentum will be minus mu1, giving a change in momentum of minus 2 mu1. Okay, so we found the change in momentum. Now what we're going to do next is to find the time between the collisions. Now the particle collides with the wall here. It's moving in a horizontal plane, so it will rebound off this wall, rebound off that wall, and come back again. And the distance it has travelled is 2lx. So it starts from here after the collision, hits this wall, and comes back again. So the time between collisions will be equal to the distance travelled, which is 2lx, divided by the speed, which is u1. Okay, so that will tell us the time between collisions. Now we can then work out the number of collisions per second. So the number of collisions that this particle makes per second is 1 second divided by the time between collisions, 2lx over u1, which is just equal to u1 over 2lx. Now we know that the force is the rate of change of momentum, so if we use that bit of physics, our change in momentum was minus 2m u1, and the number of collisions per second that we derived on the previous slide was u1 over 2lx, and putting that all together we get that minus 2m u1 squared over 2lx. Okay, and then our 2's cancel out, so we are left with m u1 squared over lx. Okay, and just a reminder that lx was the length of the box. So we've derived an equation for the force that the particle applies every second, and we can now work out the pressure, because pressure is force divided by area. Okay, and this wall here has dimensions. That is Lz, and that length is Ly. So the area of this wall here that our particle is colliding with is just Lz times Ly. So our equation now becomes mu1 squared over Lx divided by the area, which is Ly times Lz, and that simplifies down to mu1 squared over Lx times Ly times Lz. And that simplifies down very nicely, because if you look at what Lx times Ly times Lz equals, they are the dimensions of the box, which is equal to the volume of the box. So our formula for pressure becomes mu1 squared over the volume. I don't want to lose that minus sign, so I will put that back in so we haven't lost it. So there is our equation for the pressure that the particle applies to the right hand side of the wall. Now, before we move any further with this derivation, the specification at AQA 7408 specification does state that you should be able to derive the full equation, but in reality I think that you will probably only need to derive some part of it, and almost certainly it will be this first part that we've gone through, where you are just considering one particle and then coming up with an expression for the pressure. And also we have been careful to keep the minus sign in, because that appeared when we considered the change in momentum. But when moving forward, because the particles are moving in all directions, we're going to get rid of that minus sign. So let's continue with our derivation. We had the pressure exerted by one particle is mu1 squared over v, which is the volume of the box. But what would be the total pressure exerted by, if we had n number of particles? So the total pressure would be m over v. They're identical particles, they have the same mass, and we've got the speed of our first particle plus the speed of our second particle plus the speed of our third particle, and so on, depending on how many particles we've got. And we're going to say that we have n number of particles. And we're going to generalize this bit by rewriting our pressure equation that we've got so far. So we've got that we're now considering n number of particles, so n times m over v, and we're going to generalize this bit by referring to it as the mean of the square of the speeds in the x direction. So that little hat, that little bar above the u, represents the mean. So we're generalizing all these speeds by this, using this term here, which is the mean of the square of the speeds in the x direction. But in reality, all the particles are moving in all directions. They're moving in the x direction, they're moving in the y direction, and they're moving in the z direction as well. So we can say that a particle is moving with speed u, which comprises of components in the x direction and the y direction and the z direction. And using Pythagoras' theorem and three-dimensional analysis, we can say that ux squared plus uy squared plus uz squared is equal to u squared. But on average, we can say that ux squared equals uy squared equals uz squared. So we can actually say then that ux squared is 1/3 of u squared. So this is where we've got to. We've got an expression for the pressure, and we've got an expression for the mean of the square of the speeds in the x direction, and this term here is actually known as the root mean square of the speed. So we're just going to rewrite that. So that is the mean of the square of the speeds in all directions. So what we're going to do now is just get rid of our term here and substitute this new term in. So we've got P total equals nm over v, and we've got we'll put 1/3 at the front times u r ms squared. Okay, and the way that you will see this written in your data book is that PV equals 1/3 NMURMS squared. Okay, and that's it. That is the equation that we wanted to derive. Do let me know if you have any comments. Do leave them in the comment section below, and thank you very much.